Hey guys, we have finished chapter 3. We are on to chapter 4. This is actually our, fifth or sixth unit because we also reviewed linear and quadratics at the beginning of the year. We are starting some trig, so we are going to review real fast all the stuff you should have learned in geometry. So I'm going to go kind of quickly. There are more videos attached to the Delta Math assignment if you struggle with anything that I talk about today. So my first point of review is that you have to remember when you have a right triangle, the side across from the right angle is called the hypotenuse. Okay, yep, I don't know what I just spelled. Okay, I should probably restart the video, but I'm not going to. We'll see if I mess up again. And the two that make the right angle are called the leg. Leg, okay, those are both legs. One of the things we use when we do these are Pythagorean theorem, where these would both be legs. And we'd get the hypotenuse squared, so we could work backwards to find a missing leg, okay? But another thing we talk about is finding missing sides and angles by right triangle trig. And to do that, we're going to use these words opposite and adjacent. And opposite and adjacent are related to where you start. So if I call this corner theta, this is still the hypotenuse, but this angle across from me is called the opposite leg. And this one right next to where I am standing here, the closest one to my little smiley face or attached to theta, is called the adjacent leg. Okay? If I were to move that little smiley face or that theta, like up here, then this one across would be the opposite leg. This other one right next to would be the adjacent leg, because this is still the hypotenuse, okay, across from the 90. So those words should be really familiar. Now, before we go any further, you are going to need to put your calculator in degree mode today. The default for most of these is radians. So, and on the emulator, you may need to do this every time you do the right triangle trig, because it will default back to radians, I have a feeling, okay? But you go to mode, and you arrow down a couple times, you arrow over till it says degree, and you hit enter. Then at the top of your screen here, it will tell you if you are in degrees or radians, okay? If you start getting negative numbers somewhere, that probably means you're in radians. All right. So again, adjacent is next to the angle, opposite is across the triangle. Now, you probably remember these, I hope, from geometry or even before, but the definition of sine of some angle theta is the relationship between the opposite leg and the hypotenuse, okay? The relationship for cosine of some angle is the relationship between the adjacent leg and the hypotenuse. Now, because the hypotenuse is the longest side, this will always be shorter than this, so this sine is always less than 1, okay? The relationship here, the fraction, will always be less than 1. The same is true here. The leg has to be shorter than the hypotenuse, so the cosine ratio is always less than 1. But the tangent ratio, which is abbreviated TAN or tan, okay? These aren't written out anywhere, are they? Sine is spelled like that, cosine, and tangent. All right, this one is abbreviated TAN, and this relationship is the opposite leg to the adjacent leg. Now, because the two legs, we don't know which one's longer, this can actually turn out to be greater than 1, okay? So this can be anywhere between 0 and infinity, that relationship. Okay. Real quick, we're just going to revisit this idea by coming up with some fractions, but we have to know which angle we're working from. This says the tan of x, so we're standing here at x. That makes this one opposite, this one adjacent, because this is the hypotenuse. Tangent is TOA, or tangent equals opposite over adjacent. So here we'd have 12 over 9, which is the only one that can be greater than 1, remember, is tangent. If we divide those both by 3, we get 4/3 as the ratio they're looking for. All right, this one asks for the sine from C. It has to be from an acute angle, not from the right angle, okay? From the acute angle, sine is so, and that is opposite over hypotenuse, so it's 24 over 26, which if we reduce by 2 will be 12/13, is that ratio. Now, so ka toa is just one way that some teachers help you remember this. You say long O here, ka toa, okay? That's a way to help you remember it. Some teachers teach Oscar had a handful of apples. My struggle with that is that it doesn't even give you the names of the function in there, but it's the order it is on your calculator. If you look on the calculator, it always goes sine, cosine, tangent here. So sine would be Oscar had, O over H. Cosine would be a handful, A over H, or adjacent over hypotenuse. And tangent would be of apples, O over A. So that's how some teachers help remember it, okay? I just always do so ka toa. That's what I learned it. That's what sticks in my brain. All right, I'll do one more of these, I guess, and then I'm going to leave it on the notes. But if you're working from angle Z this time, you're up here. So this is opposite. This one across from the 90s, the hypotenuse. This would be adjacent. Cosine is ka. So it is adjacent over hypotenuse, which would reduce by 4 to, no, excuse me, by 7 to 4/5. There we go. We divide them both by 7, okay? I'm going to skip number 6, save time. You can go back and check it in the notes. All right, so how do we decide which ratio we're going to use? Well, we work from the angle. So if I have a triangle that looks like this, and I know this is a 26-degree angle, and I know this is 7, and this is something I'm looking for, I say from this angle, I have opposite is a 7, and maybe this was an X, on the hypotenuse. So then I have O and H, and I have to figure out which one has an O and an H, and that would mean I would need to use the sine. Okay, we're going to practice this. And here's another example. So the other thing is when you go to solve these, if you just put this over 1, then you can treat this as a cross multiply and divide question. Remember those? If you had 4 over 5 equals 7 over 8, you just go 4 times 5, or 4 times 7 equals 5 times x, and then you divided both sides by 5, so you ended up typing 4 times 7 divided by 5 to figure out x. Well, this is the same thing we're doing here. We're going to do sine of 36 times 7, and that will equal 1x. We won't need to divide, we could divide by 1. But if we have one that's set up later like this, we're going to go 9 times 1 equals, and then it's the cosine of 43x. So I just always do that division in my head, meaning that I type it I go, oh, well, these two I can multiply, but this one I have to divide. So I just do 9 times 1 is 9 divided by cosine of 43. And then that would give you your answer. All right, so I'm not asking you to type these. I just want you to think about how you're solving this so we can practice. Here we go. So first things first, we always work from the acute angle they give us. So from up here, this would be adjacent, this would be opposite, this would be hypotenuse. I have something on the H I'm trying to find and the O that I know. So O and H is sine, or so. So I write the sine of the angle that has to go in there equals O over H, or 15 over X. Now, this first one right away, the X is across from, or kitty corner from here, diagonal from the sine of 61. So if I cross multiply, going this way, I get 15, but then I have to divide by the sine of 61 to find my X. Now, if you want to write all that out, you want to do 15 times 1 is 15 equals X times the sine of 61, and then divide by the sine of 61, you are welcome to. So that's the same thing I'm going to do here. I'm going to do 15 divided by the sine of 61. Now please do this on your calculator, because if you don't get this answer, you're probably not in degrees. 15 divided by the sine of 61. Now you can close, you have to divide in this order. You can close the parenthesis, but as long as it's at the end, it's not required. So I got 17.2 if I rounded to the nearest tenth. Is that right? 0.15? Okay. Next one. For this one, I am here. So this is an adjacent leg. This is the hypotenuse. This is opposite. Well, this time I have the adjacent and I'm trying to find the opposite. So opposite and hypotenuse won't help me. The one that uses O and A is tangent. So I'm going to say the tangent of 67 degrees equals O over A. So it's X over 16 this time, which if I put this over 1, these are diagonal. And I have 1 times X, so I get X equals, and you can type the tan of 67 times 16, but if you do it in that order, you do have to remember to close the parenthesis before you put the times 16. Sometimes I just do it 16 times the tan of 67, because then if I forget to close the parenthesis, it doesn't matter. So tangent of 67 times 16, or 16 tangent of 67, and then I don't have to close the parenthesis, and I'll get the same answer. If I do the tangent of 67 times 16 and I don't close the parenthesis and I do it in that order, way wrong answer. Okay, should have been this 37.7. Now, this should make sense for our picture, okay? This is a bigger angle than this little guy, so it should be greater than 16, that kind of thing. On this picture over here, 15 was a leg, so the hypotenuse had to be longer. It was at 17. All right, a few more here. This is opposite of where we are. This is hypotenuse, so that would be sine. And opposite over hypotenuse. So I would type 17 times the sine of 24. And get 6.9. This one is a hypotenuse and it's adjacent to this angle up here. And this is hypotenuse, the one is cosine. So I have the cosine of the angle, which is 73 degrees, equals, adjacent over hypotenuse, so it's 13 over x. So this time, my x is in the denominator, so 13 times 1 is 13. And then I would have x times cosine of 73, so I'm going to end up dividing by the cosine of 73. Whenever x is in the denominator here, you have to divide. So that one is 13 divided by the cosine of 73. 44.5. Does that make sense for the picture? If we go back up here, we were looking for the hypotenuse, so it should be longer than that little side right there, right? All right, I think I have a couple more examples. I will put them in the notes, but I'm going to skip them for now. I'm going to go down to finding an angle. All right, so if you're struggling at all, please go back and do 13, 14, 15, and 16, and then check the notes. All right, how to find a missing angle? We're going to set these up the same. If this is 7 and we'll say 11, and we want to find this angle, we're going to say, and they will use theta a lot, the Greek letter here. So we are going to say, I'm standing right here. This is opposite of me. This is a hypotenuse. Opposite and hypotenuse means I need to use sine, but I don't know the angle. I just know the ratio is 7 over 11 because it's so, okay? So here you have to type second sine on your calculator, which will bring up this, and then you put in that 7/11 and it'll give you the angle in degrees. So if I get my calculator and I do second sine, put that ratio in, then it gives me 39.5 degrees. Okay, there's also an example over here. All right, so a few more of these. This one, from this angle I'm looking for, I have an adjacent and a hypotenuse, which means I'm going to use cosine. The cosine of some angle is equal to adjacent over, adjacent over hypotenuse. So when I type it in, I'm going to do second cosine of 19 over 28. Has to be less than 1, can't be 29 over 28. Second cosine, second cosine, 19 over 28, I hope I remembered that right, is 47.3, and I always round these to the tenths. Okay, I know it says nearest degree. I always do tenth. It doesn't matter if you do degree, we'll live. I don't know what it does in Delta Math, so just do whatever it says on there. This one, opposite and adjacent to this angle up here. O and A are tangent. So I would set up the tangent needs to be undone from a relationship of 9 over 25 to find the angle theta. So I would say second tan 9 over 25. Is that what it was? I can't remember. My brain is distracted. 19.8 degrees. Or 20 degrees if you were checking their answers. I'm sure they did it to the nearest degree. All right. One more or not? We got this. I'm going to say we got this. I'll go back and do these in the notes. Now, the second half of this lesson is on remembering your special right triangle patterns. Okay, those special right triangle patterns are developed. The first is from a 45, 45, 90 triangle, which means these two legs are the same length, and this is the hypotenuse. If I call this x, and I just do Pythagorean theorem to find this side, I'd have x squared plus x squared equals my missing hypotenuse squared. This would become 2x squared. If I square rooted both sides to solve for the hypotenuse, I would have the square root of 2 times the square root of x squared would be x. So this ratio is x square roots of 2. That's where that comes from, and you need to memorize that pattern. It is leg, and leg times the square root of 2 when you have a 45, 45, 90. Okay? So on this picture, the two legs are the same, so you'd have 14 and 14, and this would have to be 14 square roots of 2. You need to leave these as radicals. This is super important for trig, unfortunately, because everything we do is special right triangles, okay? This is supposed to be the leg times the square root of 2, so we're in luck if we just take the square root of 2 off, we'd have 7 and 7. These are the easy kinds, okay? They do get more complicated. The legs need to be the same on a 45, 45, 90, so you'd have another square root of 10 over 2. The hypotenuse over here should be that leg times the square root of 2. Well, this is messy. It becomes square root of 20, which becomes square root of 4 times square root of 5. And the square root of 4 is 2, and then this 2 divides out that 2, and we just get square root of 5. It's a 5, okay. So sometimes they're really messy and you have to do a bunch of calculations. This one I like to call is in disguise, okay? This is supposed to be the leg times the square root of 2, but somehow they just have a plain old 2 there. So what we have to do is divide both sides by the square root of 2. So the leg is 2 divided by the square root of 2. Unfortunately, we can't leave it that way. To get rid of that in the denominator, we need to multiply by itself, because square root of 2 times square root of 2 will be square root of 4, which is plain old 2. Up top, we have 2 square roots of 2. Well, guess what? That all simplifies down to just the square root of 2. All right, so this was, in order to make these both the same, we had to divide by square root of 2. Kind of crazy. All right, there's more trickiness when you have an equilateral triangle, because these three sides are all the same, okay? Now we could say they're all x, x, and x, which would get a little complicated. It's actually easier if you say, I'm going to split this down here, and that will take this, that used to be a 60, 60, 60, and now it's a 30, 60, 90. And I'm going to call this piece down here x, because that would make this also be x. So this whole side over here would be 2x. Then, if we pulled that triangle out, we have an x and a 2x. And if we wanted to do Pythagorean theorem to find this leg right here, we would say one leg squared plus the other leg squared equals the hypotenuse squared. X squared plus something squared equals 2x times 2x is 4x squared. So if I subtract this x squared, I get 3x squared. And then if I square root both sides, over here I get my question mark equals the square root of 3 times some x. That's where that comes from. You don't have to know that. What you have to know is how to solve this when you know that pattern. So this side is the short leg times the square root of 3. Now, students get confused and switch these around. Everybody remembers that the short leg is across from the 30, the long leg is across from the 60, and the hypotenuse is across from the 90. What students get confused about, and it's so important that you understand this, the square root of 3 is like 1.6 something. okay? 1.73, just kidding. I don't know why I didn't know that. Should have. So 2 is bigger than that, okay? So x times the square root of 3 is smaller than 2x. So the 2x is the hypotenuse. This is a leg. And then plain old x would be the short leg. All right, so we're going to use that pattern. Here it is again. This one talks about if you happen to know the hypotenuse, you would cut it in half to find the short leg here. And then the short leg times the square root of 3 always goes on the long leg. So this is how I remember it. It's short leg is x, short leg times the square root of 3 is the long leg, and the short leg times 2 is the hypotenuse. All right, so here we have, this side is supposed to be the short leg times the square root of 3. Well, if we take a square root of 3 off both those, that means the short leg is 7, which would be down here, and then twice that would be the hypotenuse, which would be 14. If we know the short leg, we double it to get the hypotenuse, which would make 8, and we multiply it times the square root of 3 to get the long leg. I hope you're remembering this from geometry. This time we have the hypotenuse, so we need to divide that by 2, and that will become the short leg, which is the y. And then once we know the short leg, you take that and multiply it by the square root of 3 to get the long leg. So we did this divided by 2 and then times square root of 3. Now, this is the hardest kind of all, because there's supposed to be something times the square root of 3 right here. The short leg v times the square root of 3. But somehow it's in disguise. If we know that v square roots of 3 equals 13, to find v, we have to multiply by, or divide, by the square root of 3. And then you can't have a square root in the denominator, so you have to multiply by a form of 1, square root of 3 over 3, because square root of 3 times square root of 3 is square root of 9, which is just 3, so we don't have a radical in the denominator anymore. The top is 13 square roots of 3, and this one doesn't reduce. So that whole mess is v. Then once we know the short leg, we double it. Well, if you double 13 square roots of 3 over 3, you multiply it by 2 over 1. So it becomes 26 square roots of 3, but still over 3. Ugh. I know these are messy. But this is what it looks like on the SAT, guys. They give you this pattern right on the SAT. But you have to be able to use it. Now I'm going to go kind of quick and do 5 or 6, and then I'm going to leave the rest for you to try. This one is the short leg, so you double it. So if I multiply that by 2, I just get 19 on the hypotenuse. But the short leg times the square root of 3 goes on the long leg. Now, please notice carefully that this is not a 30, 60, 90. This one over here is a 45, 45, 90. So these are, both the legs are the same, and the hypotenuse is 4 square roots of 2. Again, 45, 45, 90, but we're kindly given 14 square roots of 2 here, so the legs are each 14. This is a 30, 60, 90. It's actually the same question we just did, I think. Hypotenuse is 11, so this would be, short leg would be 11 halves, and 11 halves square root of 3. All right, 45, 45, 90, so both legs are the same. Ugh, that's disgusting. But if you take that and you multiply it by square root of 2 to put over here, what happens is this becomes square root of 4 or 2, and then it divides out, so we just end up with a 17 here. Legs are the same, 45, 45, 90 again, and 10 square roots of 2 times another square root of 2 is 10 square roots of 4, which is 10 times 2, or 20. All right, I'm going to do a couple more. This one is supposed to have the short leg b times the square root of 3, and somehow they hid it inside this 15, so we divide by square root of 3, which means we have to multiply by square root of 3 over 3. Square root of 3 times square root of 3 is 9, or 3, and this goes in here 5 times. So I just got b is 5 square roots of 3. And then I'm supposed to know that to get from the short leg to the hypotenuse, I double it, so it's 10 square roots of 3. Okay, easy one. This is v square roots of 3, so v is just 7, and this is 14. This would be 19, and 19 square roots of 2. This would be y times the square root of 3. Short leg times the square root of 3 gave them square root of 15. If we divide both sides by square root of 3, here we can just say that this is square root of 5. And then once you know the short leg, you double it to get the hypotenuse, so you'd have 2 square roots of 5. All right, I'm going to stop. You need to go back and check the notes, and then you need to practice all of this on Delta Math.